Okay, now we're going to continue with the gas turbine or the steam turbine, or both is the same. Of course, the media itself is going to change, but the component it is the same. Yet some of the calculation going to change due to the media that changed. Okay, we're going to study regarding, we're going to open the subject about the axial gas turbine or the steam turbine. Just to be in the picture, the axial turbine is giving high cost, or it is very costly, but it's giving very high flow for a large engine and engines, and also it is have a high efficiency. It is also difficult to maintain, by the way, the axial. Of course, there is some radial turbines. It can be like in the cars industry or something, but however, it is less cost but less flow and less efficiency, and it is easier to maintain, of course. But mainly, it is this one which is will have a lot of application of simulation or modeling, etc. It is based on either an impulse or a reaction. The impulse of the reaction, it is very simple. First, we have a guiding nozzle or guiding nozzles here, which is giving to a vanes, the rotating vanes, and also guiding nozzles and the rotating vanes. If it is an impulse, which is mean the jet push this one, and there is no any reaction happening inside, just the impulse itself. It is similar, like if you remember the built-in turbine. Okay. So area here is same like area here, and from the nozzle vanes are rotating. But the reaction turbine is area here is bigger than area here, which is making a reaction to push upward. In real case, we have both of impulsing as a nozzle plus some of changing in the areas, which is giving us impractical application. However, just a comparison, if it is an impulse, pure impulse turbine, we know at the nozzles velocity get increase, and then I'm talking about the velocity, then velocity get decrease due to the friction, then velocity get decrease also due to the friction, then velocity get decrease again due to velocity get increased due to nozzling, then velocity get decreased changing from the kinetic energy to energy as a power, then due to friction, then it decrease for changing from kinetic energy of the fluid to kinetic energy of the vanes, and the pressure of the fluid or of the gas, it will be at high pressure, then it is reduced, then it is almost constant till the end as the pressure all getting constant, because it is lost of all pressure, change all the pressure here in the nozzle to kinetic energy, so we are only absorbing the kinetic energy and transfer it to the vanes. If it is it is as a reaction, same, it is nozzles vanes, so yeah, so here is the green, so velocity get increased in the nozzle, then get decreased again because of both the changing of kinetic energy from the fluid till the vanes, and also changing the kinetic energy itself as a reaction, so it will drop back again. Then from a nozzling, it will have a pressure back again, or going to increase the velocity from the nozzling again, then it is dropped back again till the out. Okay, which is will have the pressure reduced here, change from the pressure energy to a kinetic energy, then it's still having some pressure, we're going to take the pressure again. So kinetic energy transfer, and also I am taking also nozzling. So I am taking from the pressure energy to the kinetic energy. Then nozzling again, taken from the pressure energy to kinetic energy. Then at the vein, taken from pressure energy to kinetic energy, plus transferring from the kinetic energy from the fluid to the veins itself. Okay. Sometimes we don't have a guiding only here. Sometimes we have a nozzle, vein. So it will be velocity increase due to the pressure. Then the pressure is almost constant here. Then nozzling again, taking a velocity from the pressure energy. Then transferring again to here. This is how we can understand if we have nozzle, vein, guide, nozzle, vein, or nozzle, vein, and in the reaction one, which is we know that it is nozzling in everywhere. Okay. This is just a description of the component itself to know what is the component of any gas turbine, axial or reaction or both of them, which is this will be both of them. So this is a practical case. It is reaction and impulse, because this is impulse and reaction at the same time. Now we are going to calculate what we're going to have. It is similar like before, what we discussed in the compressor, that is in P curves, and this is temperature and this is S. So at P2, so this is, by the way, this is a Brayton cycle, which is compressor heating, then a turbine, then a power output. So, which is compressor heating, pressure reduced in the turbine, then repeat the cycle again. What we are trying to get, like what we discussed before, eta isotropic, which is in the turbine. So we know from 3 to 4, 3 it is the inlet to the turbine, 4 is the outlet from the turbine. If this is actual one and this is isentropic one, same as the efficiency, we can apply it that the total what we have, which is 3 minus 4, temperature 3, of course it's multiplied by CB, and here multiplied by CB and m dot and CB, and CB, it is efficiency. Okay. So, and this is based on gases, by the way. Okay. So, not based on the steam. Steam, you cannot write temperatures. That's what we wrote here, or steam, and because steam, we cannot apply energy of the enthalpy is equal m dot CB delta T. This is only for gas, for air. But if it is for steam, no. You need to write enthalpy 3 minus enthalpy 4, because CB delta T, it is for gas, for air. Okay. So it will be enthalpies here, same equation, which is mean from 3 to 4 divided by from 3 to 4 dash. Okay. This is eta isentropic. If we remember for the compressors, it was dash minus this one divided by the actual one. Why it is like this? That's very simple. Because eta is less than 1, and because it's less than 1, so we know that is the actual power we're going to have is absolutely less than the isentropic process. And here is the same. The actual power I'm going to have, so I need to give should be bigger than the isentropic process. And even you can get it from the curve. So you can check this height and this height, just if you forget it. Okay. So, okay. Based on this, I know that this is isentropic efficiency. So I know this is the work done per mass flow rate. It is CB inlet of the turbine, which is 3, outlet of the turbine, which is 4, S, stagnation, which is equal to, as we know it before, it is V whirling velocity 2 multiply angular velocity 2 minus whirling velocity 1 multiplied by angular velocity 1, and we can open for the veins. Imagine this is a nozzle, and this is the vein. So we know by anyhow with the same angle is enter, and we know because it's pushing like this is rotating this direction. So this is U, and this is enter like this. So this is a vertical component. this is the Whirly component, or sorry, the relative velocity component in the rotation direction, and this is u combined together vector wise, so will be the rotating component, the component of v1 in the rotated direction. This is the definition. So you will find v here, so start from here, it will be here v1. And by the way, and this is v w1, vw1, it is u plus the angle here beta, so beta cosine, if this one is here like this, so this one beta, for example, so it is vr1 cosine beta plus u1, it is equal whirling velocity. Okay, now because we know that air is pushed like this, so here is a rotational velocity is equal to the rotation velocity, so we know that is u1 equal u2 by anyhow, so we can put this two outside. It is the same concept, which is air will go like this as a relative velocity, and we know this is u in this direction, so this is a vertical here, and this is here, sum of vector, which is this line, which is a whirling velocity, and v2 can get it. Okay, it is the same. This is the velocity diagram. Now, as we agreed, that is in case of dealing with the steam, same velocity diagram never change. Yet the temperatures change to enthalpy, which is mean Cb delta T, no, it will be delta enthalpy. How will you get delta enthalpy? You have either the steam tables from the thermodynamic tables, or you will open the steam graph, which is either the table or the graph. If you forgot it, steam. Okay. Yes. So this is the steam, and this is the enthalpy, and here is a mixture. Here is a subcooled saturated liquid, subcooled liquid, saturated vapor, superheated vapor, and in case we are dealing with steam turbine, so it will be bump. So you will have a bump here, increasing pressure like this till a point, then it will go straight, which is heating in the boiler with this constant pressure. Then you will find expansion like this, then or heating like this, then it will go down. Okay, which is a steam turbine, a boiler system or steam turbine system. However, we just need to get the two enthalpies in and out to get it. Okay. Okay, now we need to identify some of the parameters that is may needed to be asked in the modeling itself. So each state, each stage area must increase than the previous area. What? Why? Which is mean here this area should be less than this, or this area should be bigger than this one. Why? Which is mean, open the paint. If you remember, we are making the turbines is simple. Why? Because here there is a nozzles, guiding vanes, or nozzles, rotating vanes, nozzle, rotating vanes. So when we are going like this, the flow, always the vanes needed to be bigger, or the area should be bigger. Why? For simple reason, we know that is m dot is equal constant, and we know m dot equal rho v area, and we know that is because the pressure going down, and the density is equal pressure divided by RT. So when the pressure go down, of course the temperature will go down by the way, but also density go down. So because density go down, m dot is equal constant, so and also the velocity go down. Why? Because I'm just was repeating it. The velocity is going down. Of course, here we're trying to increase it, but yet it is going down at the end. At the end, the velocity in this stage is less than this stage, by the way. So, which is mean out of the rotating vane here, and when it is out of the rotating vane, however, so we know that the velocity getting decreased. So also the velocity going to be decreased at later stages. So based on this, area must be increased. So if this one down, this one down, this one constant, so area must increase to adapt it. In another way, by logic, when density get decreased, more volume is needed. And also the velocity is decreased. So that more volume is moving even slowly, so it will take more, the flow rate will take, mass flow will take more and more volume, which is you need more area to adapt all of this. Okay, this is just by logic. Okay, but also take an account that the blade length based on this, to make the area increase, you need to make the blade length more, which is mean this one needed to be more. Imagine this one is rotating like this, so there is plates, so there is plates like this coming from here, which is the nozzle hitting it, then it is rotate. So which is mean because this area is bigger, so the diameter is bigger, which is mean the length is bigger of the plate. Okay, logic, it's okay, no problem. So when the plate must have bigger length, something happen. We need to twist the plate to what? To ensure there is no stresses on the plate. You will tell me what? Why? See, listen. Here is a plate. I will imagine that as we already increase the plate length. Okay, and here is a nozzle. So flow, 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 and the plate is taking shape like this or whatever. Okay, so based on this flow, I know by default that here is the curvature is something, here is a curvature is something else, here is a curvature is something, here is a curvature is something else. So angles change. Yes, so angles change. What's the problem? So let's study it, please. At the hub, at the mean, at the tip. At the hub, it should be twisted. Why? Because the inlet, when it is go here, it will rotate, by the way. This one is rotated like this out of the page to enter to the page. So based on that, here u velocity is something, and here u velocity is something else. See? So our assumption here, which is u equal constant, start to be incorrect. Okay? Of course, this one, imagine it, that is, there is a center here of rotation in middle, far away, inside the paper, and going up till here, and there is a lengthy nozzle also as well. So we make a cross section. Okay, so u is going to change because the blades change of the length. Okay, so at the hub, which is mean it's very low when the air enter here and go out here, because this one, as we said, is rotated. Here u is small, and when the air here u is big. So based on this, when u is small and you can draw it, if you didn't twist the plate at the bottom, so the angle will reduce the whirling velocity, and the same manner here, and the same manner here. So in the hub, or in the start, you need to twist the plate a lot. Why? To make here if you twist the blade a lot, you will make the whirling velocity bigger. If you make this one like this, so the angle of the blade here is like this, so the whirling velocity will be just from here to here. But because I know in the tip it is actually like this, so it is required to twist the blade on the hub and keep it normal on the top. How it look like? It will be like this. Twist the vanes in the gas turbine. Yeah, yes, something like this. So I need it. Okay. I need one photo which is to be simple. Okay, we'll try to zoom in here. No. However, here you can, no, it is not. Yeah, okay, here it is way perfect. You see here it is twisted like this, and the angle change when you go. So here is the angle is something, here is the angle is something else, which is mean twisting the blade. Why we doing it? To get what? To get an equal whirling velocity. If you have an equal whirling velocity, so no stress is going to happen, because whirling velocity is what? Whirling velocity is amount of energy is going to hit the blade to generate the power. So if I have here a lot of force going to hit and little bit force here, so it will be stresses on the blade itself. So we're trying to keep it as equal as also by twisting the blade. Okay, just to be in the picture, like sometimes we tell you, okay, you will do some several simulation for certain blades angle twisting, just to check what is there is a stress or no. One of the ways to get there is no stress or no, check the whirling velocities at each point is almost the same or no. Okay, so if it's like the model is created to check the stresses, you can ensure it by the velocity itself. There's no stresses or no. Okay. Now it is the gas turbine is finished, and we are going to continue later on cavitation. We finish it. There is one about the looping analysis and the system curves, and one is the compressible. So in the compressors itself, the operation itself for the compressors, and concentration. Okay, let's go one by one. We're going to discuss about system curve. For any system curve, its definition, it is head of the system curve at a certain flow rate. It is an equation of a H static. It is a constant, which is, for example, if your pump is giving a water with head static up or down, down with minus, up with plus, it is K, which is a constant representing the losses in the system multiplied by Q square. I already discussed about how we got it, this one, if we remember it. Where is the control volume? About H losses, I remember that we open it. Potential flow, basic ways, yes. Remember when we write that is H losses is equal blah blah blah, and we write it here that is K fitting or H loss fitting. It is K divided by 2G velocity squared. So K divided by 2G, it is still a constant. So it is for fitting, and we assume it also not only for fitting, we assume it also for a certain, for example, a friction loss here for a turbulent flow. It is based on the diameter or the hydraulic diameter by epsilon, and this is constant. Okay. So we can assume that the coefficient of friction is constant. If it is smooth pipe, it is with a relation with the Reynolds number, and Reynolds number is relation with velocity. However, for approximation, we can state that this one is still a constant or defined with as it's a certain diameter. So we will deal with the entire system as like it is a one piece of pipe, piece of fitting, and to get K total. Okay, multiply by Q square. Q square, it is area multiply, which is taking effect of the diameter itself. Okay, K, how we calculate K? K, it is 1 over 2 G area square, because Q, it is equal what? Area square multiplied by V square, and I need to reach at the end K multiplied by V square over 2G, okay? So K, it is 1 over 2G area square multiplied by the losses of the valve, the losses of the bend, the losses of the all. You need to count it all, sigma, count it all, each bend, each valve, and total friction or coefficient friction divided by D multiplied by the length of that D plus the other pipe plus other pipe. Of course, you will take the longest run. When you will go take the longest run to calculate all the keys. When you calculate all the keys in the longest run, whatever you're going to change in the flow rate, what will happen? You will get a system curve, which is if you intersect it with the bump curve, you will have the duty point. Okay. Of course, when less K or when less losses curve go down, when high losses curve go up. Okay. Okay. Compressible flow approximation. Compressible flow approximation, we understand this is we need to use our concept for thermodynamics regarding convergent divergent ducts, or you can do some approximation. If you have a certain pipe flow and you know that it is very high pressure and it is reducing the pressure and the velocity is over 0.3 Pascal, and you don't want to go in hassles of the thermodynamic solutions, and you was trying to go like a quick approximation, by the way, a quick approximation, but it is a technique which is valid, but it's a quick approximation. It is naming like you're going to divide your length of pipe in I's, and you deal in this length of pipes as what is the pressure loss between here and here, and with the new pressure you calculate the new density and you continue again. How? For example, you will say from 1 to I, so B1 minus BI, it is Bernoulli, by the way, plus Z here plus Z here is equal what? Is equal to the friction loss, by the way. This is the equation of the friction loss. Of course, it is an approximation equation for the friction loss in a pipes. Okay, from this equation you will get BI. From BI, you know OI, BI equal over RTI. Then you repeat it again. I is a 1 now, and 2 is, and I is a 2. So 1 is I, and change I to 2. So from here to here, you calculate the new pressure. When you make a lot of divisions, you can make the pressure. You can use it Excel. You can use even a software or something. Okay. Okay, it's just an approximation, by the way. Okay, for double checking. This is another technique. It's not related to the CFD at all, but we can just describe it in the way. It has no any relation with CFD. There is another software which is calculating this, like by flow or Bentley water, or other similar softwares like Elite, etc., which is doing the hydraulic calculation based on looping analysis. Looping analysis, which means you have 1, 2 point inlet or bumps, etc., but you don't know from where the pipe is going, the water is going to go. Because, for example, here the water can go from here to here, or the water can go from here to here and loop again. You don't know. So we name something as looping analysis. I know it's not related to CFD, but we're going to open it. For each pipe, we need, or we can define the resistance of the pipe, which is 0.8 coefficient friction multiplied by L by over GD over 5. So we assume the flow rate direction. At each pump, we need to provide a flow. We need to say, okay, the flow here will be like this. of course we cannot do it, but you need to say, okay, the flow here it is 100. Of course you cannot reach the flow here is 100 because it is depending on the longest run. However, I'm going to tell you what to do, but we need to fix it. And then we need to know what is the height of the tank. So not in transient mode, at still it's like a certain point, okay, with a shape of also with the height of the tanks. Any between tanks make one dummy line with zero flow, and you need to assume a rotation. Okay, say okay, the rotation always like this, the rotation always like this. If the flow with the rotation, it is in positive. If the flow against the rotation, it is in negative. Okay, simple. Then you calculate Q naught, which is mean the first trial. Okay, multiply by Q naught over n minus 1. Q, it will be positive or negative according to the direction. Here there's no any meaning of positive or negative because this is magnitude in positive amount. N minus 1, which is trial what you are doing. Okay, then you calculate this one for each loop. For example, this loop has pipe 3, 2, 6, and 4. This loop has 5, 6, and 1, and 7. So you put it 6, 4, 2, 6, okay. Then you will put it, and this is for loop 1. You make the same schedule for loop 2, etc. Then you make the sigma. All these numbers added together here. All this number added together here. Name this one as a K. Name this L, and write delta Q1 for the first table is minus K over L. Delta Q2 for the other loop. And maybe you have 3th loop, 4th loop, 5th loop. So you will find this number, delta Qi, delta Q double I, etc. Then you make the correction. What is the correction? Is you know that is the Q assumed. You already assumed the Q here. You said that is this one equal 1. You assume the Q, okay? You see the Q assumed plus or minus whatever here you are getting, plus or minus whatever here you are getting. And this will be the new Q. You will repeat it for all. And the Q which you know, it is should be 0, okay? Okay. And of course, here, delta Q I only you're going to affect. Here, delta Q I and double I. Okay, so here delta Qi and double I, for example, for 6, here will be delta Qi only. Okay, which is shared, delta Q is a both, which is not shared, not. Then you will repeat. Then you will repeat. Then you will repeat till you will reach this one is almost 0. Then you stop, and this is your condition. After you saw all of this, you see where is the longest run with the maximum head loss. You calculate the entire pressure loss. Then you calculate K, and based on the Q, whatever, you don't know the Q till now, and you know that what is the static. Then you draw the system curve. You intersect it with the pump curve for this pump. Then you check is the flow which is you already stated running with the pump is correct or no. If it is correct, voila. If not, so there's a new flow here. So you'll repeat the whole process again. It is a lengthy procedure. That's why it is better to do it with hydraulic calculations. Sorry, hydraulic modeling. Now we are going to discuss about the compressor itself. There is some condition in the compressors, which is, or fans even, whatever, but mainly the compressor. Surging, shocking, and stall. Surging and stall is almost the same, shocking something else. Okay. Imagine that you have a fan curve or a compressor curve, and this is a pressure ratio, or whatever pressure you're going to get, or the head outside, and this is the mass flow rate, or the Q, which is a volumetric flow rate, or etc. Okay, a flow rate. A, it is simple, where is no flow. C, with no pressure. It is impossible, by the way, at no pressure there is a flow. It is impossible, that is, okay? So usually it is like this, and stop somewhere here, okay? Okay. Let's agree about something. This point is shocking. What's mean shocking? Sorry, let's stop here. What's mean shocking? That's mean the compressor outlet or the diffuser or anywhere inside the compressor has been shocked. It reached to Mach number equal 1. When it's reached Mach number equal 1, we remember from thermodynamics, you cannot increase the mass flow rate, whatever you're going to do. So the curve should stop here. There is nothing, you cannot go after the shocking point. And we should not assume we can reach nearby even the shock. So our system curve should be here. If the system curve is very near to this one, we should not do it. Okay. Point number B. Point number B is the surge limit, which is mean. What does mean surge limit? Surge limit, that is the pressure drop ratio. Again, we discussed it before when we were speaking about forward curved fans or plate. Yep, here when we start say till this point from here to here, don't select. Why? It is almost the same concept, but it is severe, way severe in the compressor. Or not in the pump, of course, in the compressor or in the fans. Because see, if your operating point here, it is okay. But what will happen if you change the operating point left or right for any reason? VEV closed or some valve is closed in front of the compressor, etc. What will happen? Or opposite side, it is open or whatever. So the pressure ratio downstream is higher, so the backflow, what will happen? The backflow will make reverse flow, which is mean if I am here and I want to go at part load, I am here, system curve, and I want to go part load, which is mean less flow rate, so I will go to D. Okay, but when I go to D, you can find that when I'm going back, you will find that the compressor giving a pressure here, but the entire pipe or entire duct or whatever having pressure here. So imagine that the compressor is giving a pressure with, for example, 1000 Pascal, for example, or 2000 Pascal, and the pressure inside the duct is 3000 Pascal. So the flow rate will never go. And reverse flow will happen back again to the compressor. Then you will start say like this, which is mean there's a reverse flow, then push it again, and it will not be a steady run. So noting at part load, downstream is higher, so backflow, then a forward flow, then a backflow, then a forward flow, and it is happen at high HZ, and happen at the diffusers, and it is we name it. Oh, it is named isolation, or it is going to isolate, or going to make like this. Okay. In the opposite case, if we increase the mass flow after B, so if we are here, but we increased after B, it is safe. Why? Whatever we're going after B, the pressure is still under B. The pressure is still under B. So it is safe. Why? Same concept. In case, if we increase in after B, pressure ratio reduce, so backflow, so no safe. No backflow, so no safe. So we are safe. Okay, no surge, which is safe. So the surge is the isolation of the in and out. Again, we are here, then part load will start to be here. Okay. So what will happen? We are here, part load will go here. What will happen? But in the opposite case, if we increase after B, pressure reduce. so it will be safe. Okay. I will draw it, maybe it will be better to understand it. Okay, imagine this is a HQ curve. Imagine that is we have already a system curve here, and this is point B. So our system curve is after B. At the part load, what will happen? It will be like this. So the new pressure is higher than the old pressure, so it will still going to overcome the duct. But imagine here, if I go before B, or even like this, it will be appear. So the pressure here, maybe, or it is maybe, I didn't draw it correctly, will be less than the pressure at B, which is the compressor cannot overcome the high pressure here. Okay, surge will happen, which is isolation. Okay. Okay. Stall. Stall, it is a phenomena which is happened to a certain vein. A certain vein, not the full veins, not everything. It is a certain vein. It can be for all veins. At that time, it will be the stall will be a surge. What is happening? When you are rotating or a rotating stall, or the stall is going to happen, which is at the time of separation. Remember, stall is separation, which means there is a separation with separation cause, what we already discussed, that is pressure is higher at the after, so some reverse vortex can happen. When the reverse vortex comes and this rotating, so the stall is rotated from vein to vein, from vein to vein. The same condition, because it's the same problem. But if the stall going to cover all of it, what will happen? The pressure reduced by the compressor get less. When the pressure reduced by the compressor get less, and the downstream pressure is high, so isolation going to happen, which is surge. And of course, this one, it is due to the angle of attack, which is creating that. Okay. Okay. Now we are going to discuss a new chapter at all, and it will be in the next session.